what we're going to do now is there are patterns to how things behave. Okay? And by recognizing those patterns, we know a pattern to how they behave, it'll let us figure out what it's going to do. So we're going to learn different types of reactions, because once we can say what type it is, then we can finish and figure out what it's going to make. So by figuring out what category it's in, we'll be able to figure out what its products are going to be. Because we're learning what you expected to learn in a chemistry class. What happens when you mix these two chemicals? That's probably what you thought you were going to learn. Well, we now know enough for you to be able to figure out what you're going to make when you mix these things. Okay? That's why we're doing types of reactions. Okay. So, first of all, the reason why is because the only other option is to memorize every reaction that ever occurs. And think about how many millions of chemicals there are. Every one of those can go through a bunch of reactions. There's no way you can remember them all. Okay? So, just like it's hard to remember every rule about how to spell stuff, or remember how to spell every word, there's some rules that help you. I before E, except after C, right? Or is it A, like in neighbor or way? Okay? General rules are easier to apply than memorizing every specific instance. We're going to learn 5 types. We're going to learn how to recognize them. And once we recognize them, then we'll be able to predict the products. Okay. What are these things going to do? Okay. Now, sometimes the answer is nothing happens. Okay? Sometimes, I mean, if you were making a boat out of metal, you wouldn't want to make it out of a metal that reacted with water. It would be important to find out which metals didn't react with water. Okay? And if we're going to predict the products, we have to be able to recognize them from just the reactants. Right? So we're going to have to be able to look at the reactants, and from what the reactants are, tell what kind it is. And luckily for us, the names are really descriptive. If you put the name on it, that tells you what it's going to do. Whatever name you gave to it, that's what's going to happen. Okay, so we're going to have to figure out what they are from just the reactants. So type 1. It's called a combination reaction. Think about the picture you would draw if somebody asked you to combine things. What would you do? What would your picture look like? Somebody asked you to show a picture that showed combining. What would it show? Taking separate things and putting them together, right? That's what the combination reaction is. Taking separate things and putting them together. So you're going to start off with 2 things and end up with 1. Okay. So here's an example. Calcium and oxygen make calcium oxide. Okay, because I haven't balanced it yet. Okay. Okay. All I said was calcium and oxygen make calcium oxide, which is what that says, right? Calcium and oxygen makes calcium oxide. Okay. It bugs me to see it not balanced. Right? Everybody see the two O's over here? That means I'm going to need two O's on the other side, right? So I put two there. That means I've got two CAs now. So I need a two there. So I don't have to make the table every time, but I want the table in my toolbox when they get ugly. Does that make sense? Okay. I didn't need I didn't get lost here. It was pretty straightforward. You don't need the table. The table's there if they get nasty. And you have to do one like this. Then you start saying, oh, I really need to keep track of what's going on. Right? 14 O's, where the heck did that come from? Okay, here's another one. Now, this is two compounds coming together. Sulfur trioxide and water. This one actually was the cause of the big environmental concern 10 years ago. 10 years ago, the big environmental concern was acid rain. Acid rain. Okay? So what acid rain is when you burn coal, there's usually some sulfur impurities in it. And that sulfur makes sulfur trioxide. Sulfur trioxide goes up the smokestack and runs into the clouds where it turns into sulfuric acid. Okay? Now, it's pretty dilute sulfuric acid, but that means the pH is lower on the rain that's coming down, and it's enough to eat away at marble buildings and statues, so it's wiping out the Parthenon in Greece. It's wiping out all the statues in Greece unless they cover them. It makes pine trees more susceptible to frost. So in the Blue Ridge Mountains, whole bunches of forests killed. In Bavaria, whole bunches of forests died out because frost killed them because the acid rain changed the pH and they couldn't fight off frost anymore. So that was the big concern when I first started teaching was, what are we going to do about acid rain? Now in California, we don't have to worry about it because there's nobody west of us making sulfur trioxide. But the sulfur trioxide we make lands in the Midwest. Make sense? So now they're trying to make machines that catch the SO3 before it goes up into the clouds. Okay? Make sense? So now, these are two different kinds of compounds. Oh, let's balance this one. Well, that was hard. 1s, 2 H's, 2 H's. 3 and 1 is 4 O's, 4 O's. Sometimes they're already balanced. Now, can you see the first one is two elements making a compound, and the second one is two compounds making one compound. There's a difference there. If I tell you, if it's just two elements, you can predict the products. Because the only way two elements can change is to come together. If it's two compounds, I would have to tell you that it's a combination. So, magnesium and nitrogen. Okay. To recognize this as a combination reaction, the only way for magnesium to nitrogen to change from where they're at is instead of being separate, come together. That makes sense? That's the only way they can change. So I need to write the formula on the other side. Magnesium's the positive part. Nitrogen's the negative part. Okay? So I did what the name says. I combined them. Now I got to write the right formulas. Mg is in the 2+ column. alkaline earth metal. Nitrogen is in the 3 minus column, group 5A. Those don't add up to 0, so Mg3 N2 do the crisscross. Then it bugs me because I have not balanced. Got 1 Mg on that side and 3 on this side, so I'm going to put a 3 in front of Mg. Got 1 N2, 2 N's and 2 N's on both sides, so we're balanced now. But think about, get used to that process. Do what the name says, combine them. Figure out the right formulas, use charges, then balance. Because if I tried to balance without doing charges, if I tried to do it without doing charges, I wouldn't be describing the right stuff. So, what would I make if I put together calcium and chloride? Calcium and chlorine. Well, there's 2 of them, and calcium is the positive piece. So calcium gets written first. It's in group 2A, so it's 2 plus. Chloride is Cl. Chlorine is Cl. It's in group 7A, it's 1 minus. It doesn't add up to 0. So I do a crisscross, put the 1 there, and put the 2 there. And then that's the right formula. So I did what the name said, put the 2 together, use charges to figure out the bottom, and now I need to balance. Well, sometimes it's easy. Ca, Ca, 2 Cls, 2 Cls, we're done. Doesn't always happen, but sometimes it does, just randomly. This time I did something different. I told you what you were going to make. Why? Well, here's why. Because if I didn't tell you, you'd say, okay, Fe is the positive piece and O is the negative piece. I go to get charges. I know O is -2. What's the charge on Fe? If I don't write that, you don't know, right? So if it's a transition metal, I have to tell you what charge it's going to make. Right? Transition metals, I need to tell you the charge. So I didn't have to tell you calcium chloride on the last slide because we could figure it out. Here, because iron can take multiple charges, so I had to tell you which iron I wanted you to do. Okay? But because they wrote this, I can put 2 plus there. 2 plus, 2 minus, that adds up to 0. Yeah. Yep. So we got the right formula for iron 2 oxide. Now we need to balance. Okay? So balancing always comes last. So I needed 2 O's, so I put 2 in front of FeO, and then 2 in front of Fe. You're tempted to do this. I'm telling you, you're tempted to it. Oops, I don't know if this thing will work. You're tempted to do Fe plus O2 makes FeO2. Boy, that makes it easy. Except there's no such thing as FeO2. You're living in a pretend universe. Okay? There's no iron 2 oxide, or iron 4 oxide. It doesn't exist. You can't make it. Okay? So, one last one, could be the nastiest one. Aluminum and oxygen. And I recognize it's a combination reaction because it's got just 2 elements. The only way those are going to change is to come together. Aluminum's the positive piece, so I write it first. Oxygen's the negative piece. Aluminum, that's the right, so I combine them. Aluminum next to oxygen. Then I write the right formulas. Al is 3 plus, O is 2 minus. So it's Al2, O3. Then I go to balance, 2 aluminums over here, so I want to put a 2 there. Then I go to fix my oxygen, and there's 2 on this side and 3 on that side. Can I get 3 on the reactant side? Why not? Because one side is even, the other side is odd. So what did I say to do? Double, whatever's in front, double it. So there was a 2, I erase it and make it a 4. That gives me 4 aluminums. So I have to put a 2 in front of Al2O3. That gives me 6 oxygens. So I put a 3 in front of O2. Reasonable? Okay, first you write the formula, then balance. People are tempted to write Al plus O2 makes AlO2. But if you look, that won't form because aluminum is 3 plus and O is 2 minus, and they won't equal 0. If you go online and look at practice of these, oftentimes they call this the synthesis reaction. Okay, so that's what happens if you combine two elements. I gave you an example, the acid rain example, where they combine compounds. Okay, so what if you're combining 2 compounds? Okay, first of all, they'll have to tell you that it's combination. You won't be able to recognize just by looking at it as combination. Yeah. What? Oh, acid rain can't burn you. It's not enough to hurt you. It just changes the pH enough to make so fish can't live. Kills off the fish. Messes up their osmotic pressures. Stuff from biology last year. Acid rain's not fatal. It just to us it just destroys stuff like buildings, marble, limestone. Okay. So if you got 2 compounds, that means you got something with 2 capital letters and something else with 2 capital letters. And when I put them together, I'm going to have more than 2 capital letters. That seem reasonable? Something with 2 elements, something else with 2 elements. When I put it together, I'm going to have more than 2 elements. And the only way we know how to write something that's got more than 2 elements is if there's a polyatomic element, a polyatomic ion in it. It's the only way so you got to look at what polyatomic ion could you make out of those pieces. For example, carbon dioxide and water. What's it going to make? Well, first of all, I have to tell you it's combination. And then I have to look what polyatomic ions can I make out of those elements. Well, there's 2. There's OH minus, and there's CO3 2 minus. Those are the 2 possible polyatomic ions I can make out of those. And I looked on the list and said, which ones can I make out of the H's, O's, and C's? Okay? Now, if I pick this, that OH minus, I'd have to have something positive put next to it. Is there anything positive on that other side, any metals on the other side that I could use if I used OH minus? Okay, if I pick the CO3 2 minus, is there something positive I could put in front of that? H can be positive, right? H is in group 1A. So of the 2, I can make CO3 with a 2 minus, and I can put the H in front. See, I'm using just the elements they gave me, and I found the polyatomic ion that matches, and then I've got a positive piece that can go with it. And H is 1 plus, and CO3 is 2 minus. So notice I did what I said. I combined them. Did I have to write the right formula? H2CO3. And then I have to balance it. If you've done this right, it will balance really, really easy. Like this. 1 C on that side, 1 C on this side. 2 O's and 1 more makes 3 O's on the reactant side, 3 O's on the product side. 2 H's on the reactant side. 2 H's on the product side. They're all balanced. You do this right, it'll balance easy. Here's about the nastiest one I could give you. Water plus dichlorine heptoxide. And it turns out there's a whole bunch of polyatomic ions that have chlorine and oxygen in them. And I have to pick one. Okay? If you look at the things, how many CLs do I have? 2. How many O's do I have? 8, right? So which of these makes sense for 2 CLs and 8 O's? The ClO4 makes sense for 2 CLs and 8 O's, right? It's the same ratio. So I put ClO4 with a 1 minus. I can put that H plus in front of it, just like before. Now 1 plus and 1 minus equals 0. So that's the right formula. Then I go to balances. I got 2 H's, so I got to put a 2 in front of HClO4. That gives me 2 Cl's, which I wanted, and 8 O's, which I wanted. So if you pick the right polyatomic ion, they balance fast. Okay? Make sense? Okay. So again, you just see what polyatomic ions can I make out of all those pieces. You have to list which one shows up. Okay, that's type 1. Type 2 is called decomposition. What happens when something decomposes? Dissolves. Does it always dissolve? Breaks apart, right? It's in lots of pieces when it's done, right? Decompose means to fall apart. And if you fall apart, you make more pieces than you started with. So one reactant falls apart into 2 or more compounds. Or 2 or more elements or compounds. Most often it's going to be elements, can be compounds. So if I pass electricity through sodium chloride, what happens to sodium chloride is it was hooked together, now it's separate. So I make sodium and chlorine. Sodium can be by ourselves, it's not one of the 7. Chlorine can't be by itself, it is one of the 7. So I separated them, wrote the right formulas, now I have to balance. To get my 2 CLs, I've got to put a 2 in front of NaCl, then a 2 in front of Na. But I went through that same process. The name said decompose, fell apart. What could fall apart into? Na and Cl. Can Na be by itself? Yes. Can Cl be by itself? No. Put the 2, then balance. So we're still figuring out the subscripts. Okay. And calcium carbonate. Calcium carbonate is limestone. The Romans heated up limestone and made lime. CaO is called lime. And lime is a big component of their cement. So one of the reasons why they went to England is lots of limestone laying around at the surface, easy to get to. Good place to make lime. Cut down all the forest in Britain because you have to heat it to make it happen. So a bunch of the forest got used up to heat the limestone to make lime so the Romans could make cement. And burning the wood gave off CO2, and making the limestone gave off CO2, so they were contributing to global warming. Making cement still is a major contributor to global warming. And so one piece makes two, decomposition. Okay? All right, so if it's just a binary compound, if it's just made up of two elements, we can predict what it's going to make. It wasn't hard to figure out that NaCl was going to make Na and Cl. You only got two elements, and you're going to change. The only way you can change is not be together anymore. So, okay, H2O, two capital letters, a binary compound. You pass electricity through water. What can you make? Well, what elements are in water? Hydrogen and oxygen. So that's H and O. That's the elements that are there. Now, write the right formulas. Does H get a little 2? Yep, it's a gen, hydrogen. Does O get a little 2? Yeah, it's a gen, oxygen. So water falls apart into hydrogen and oxygen. Now I need to balance. The oxygens are messed up. 1 oxygen on the reactant side, 2 on the product side. So I'm going to put a 2 in front of water. That gives me 2 oxygens there. It also gives me 4 hydrogens, so I put a 2 in front of hydrogen. Gives me 4 hydrogens. And that says water makes hydrogen and oxygen, but 2 water molecules make 2 hydrogen molecules and 1 oxygen molecule. Maybe we could see that happen, like right over there. Isn't that what I'm doing? Passing electricity through water? Is that what I said I was doing when we started this? Hey, and I've collected some gas. Okay? My tubes are full. Collected some gas. But you'll notice that one side, the gas is down this far, the other side is down this far. There's twice as much gas in this one as in that one. I can actually read the numbers. There's actually twice as much gas on one side as the other. Why would there be twice as much on one side as the other? Okay. It says 2H2 and O2, right? So, if my equation says that, that means that if there's twice as much of this gas, this side should be hydrogen. See reasonable? Twice as much. It says I make twice as much hydrogen. Well, one thing we know about hydrogen is it's flammable. Right? So what I'm going to do is I'm going to take some of this gas. I also know that it's less dense than air. Now, stay in the test tube upside down until I flip it open. Okay. A little bit hard to see, but this actually is frosty on the inside. There's condensation on the inside of this test tube. Why would there be condensation on the inside of the test tube? Oxygen? What did I put tear the water apart into hydrogen and oxygen. Get energy back out, then the hydrogen and oxygen turn back into water. And that's the relationship between combination and decomposition. They're just backwards from each other. And what usually decides which way you go is whether you're putting energy in or getting energy out. Okay? So to make the hydrogen for cars, they do this. They pump it up at high pressure and put it into a tank. When the hydrogen car drives down the road, out the tailpipe comes water. Okay? So just one more time. That's hydrogen. The other side is supposed to be oxygen. This was a little harder to pull off. Let's see if I can get it to work. And what do we know about oxygen? Well, oxygen makes things burn well. Right? So I'm going to take a toothpick and light it on fire. And then I'm going to blow it out. So just the end is low. Okay, pull. And then I'm going to let this side out. See, you've got to be careful. Nice mine. Toothpick back up. It makes things burn better. Oxygen makes things burn better. Okay? So what I'm trying to say is, those letters and numbers we're writing on the screen are describing what really happened. Right? This is not like math class where you get an answer that doesn't mean anything. This says, I'm going to make gases. I'm going to make twice as much hydrogen to make oxygen. Okay. What about HGO when heated? Well, that's mercury 2 oxide. What elements are in mercury 2 oxide? Well, mercury and oxygen. Okay, now we decide, do they get 2s? Well, the oxygen gets a 2. Does mercury get a 2? Nope. So I've got the right formulas. Then I have balance. So do what the name says, decompose them, figure out the little numbers on the bottom. Do they get 2s? Then balance. HGO is, I got 1 O, so I need 2 HGs, HGOs, because that gives me 2 O's. It gives me 2 HGs, so I put a 2 there. Okay. So tonight you'll read about combination decomposition reactions. The other 3 type, which is single replacement, double replacement, and combustion. Okay. We'll read about those in 11.2. Okay. We'll come back on Monday, Tuesday we come back. We'll do some more combination decomposition, give some practice doing those examples. But I wanted to get a sense of why we learn types. Why we're doing that is so we can predict what's going to happen. Okay. Stay dry for the next couple of days. It's supposed to stop about 4 o'clock this afternoon. If you practice balancing, it's taking you time, or if you're getting them wrong. I saw some people on the things. You need to go practice more. Put some practice sites up there for you. Have a great weekend. Hey, is that sunshine? Bye, take care.